Now that we've seen a glimpse of the state space for this system, let's see how we construct it in MATLAB, and then we can go on to see what happens if we perturb the initial conditions and the parameters. So first, I just want to quickly revisit the state space model that we have for this system. Again, we have 3 state variables, so our left-hand side is the derivative of each of those state variables. So I'm going to put this state space model into MATLAB, and again, I can't use matrix form, but we'll see how we can still use ODE 4.5 or similar solvers to solve this nonlinear system of equations. So going into MATLAB here, I'm going to start with the M file that just creates the x dot, the derivatives of my 3 state variables. So it looks in form similar to what we saw, or the same as what we saw really for linear systems. I have to name this function. I'm going to name this Lorenz. It's going to take a time input. Here I just have it as a tilde since time does not appear explicitly in any of my equations. There's no forcing, but I could put a t there. It's not going to matter for this. So t or tilde, then what I'm naming my state variables in the function, x, for this one. And in this case, I have 3 additional arguments or parameters, rho, sigma, beta, that I'll be able to feed this. But the important thing is I'm going to always put the order t if needed, the name of my state variable, and then parameters. And then the output is what I'm calling xd. Always the output function has to be the vector of derivatives of my state variables. And importantly, as we'll see in line 3, this must be a column vector. Now, when we're doing this in matrix form and we're making that A matrix and we're just saying A times X, as long as X comes in the right size, it's going to go out the right size as X dot. So it wasn't as big a concern. When we're working with these nonlinear systems, or when we're not using matrices, let's just say, we do want to do what I'm doing in line 3, where I'm pre-allocating the shape and size of X dot. So I am saying initially it's just 0, 0, 0, but notice here I'm making it a column of zeros. Right? So it's a column of 3 zeros. I need as many zeros or entries as I have state variables. So this ensures that when it goes out, it will also be a column vector. If you do it as a row, it's not going to work correctly. Now, in 5, 6, 7, I'm defining individually each element of x dot, what I'm calling xd. Right, so xd of 1, the first entry, this is going to correspond to x dot in my system of equations. This is my x1, is sigma times y minus x. Here, y I'm mapping to x sub 2, and x is being mapped to x sub 1. Then quickly flashing back here to our system of equations, this is exactly that first line. Again, I'm assigning x to x1, y to x2, and z to x3. Now I can move on to my second line, my y dot line. Right, so it's x times quantity rho minus z minus y. So I'm now going to map that into my M file. And that's being done on line 6. I'm individually saying the second element, x2 dot, is what the left-hand side is really saying, is x1 times quantity rho minus x3, which is z, minus, here I have x2, which is y in that original equation. So I did have to convert into the state space form, which I'm not showing that step, but that's what's happening here. And then the third equation, once again coming from this original set, z dot, which I'm calling x3 dot, equals x times y minus beta times z. And looking at it in the MATLAB form, I have x times y minus beta times z. Okay, so I've defined each element now of xd, the first, the second, and the third, which correspond to x1 dot, x2 dot, x3 dot, which is to say x dot, y dot, z dot in my original names of my coordinates. So this is how I set up my function for nonlinear ODEs. Or I could have done this for the linear ones also by individually saying what x dot 1, 2, 3, 4 was, but the matrix form was just much easier for that. So now let's see, how do we use this and also answer or investigate some questions about this nonlinear system. So while solving this, we're also going to see how perturbations are going to affect this nonlinear system. So first we're going to consider this, and this is, I'll get much more into this later, But the instruments we use in this example, let's say for weather forecasting, have finite precision. So our thermometers, our hygrometers, our barometers are all going to be capable of only so many digits of precision. And that's important because when we're putting in our initial temperature, air pressure, and humidity, the precision at which we put it in might have an impact on the system. And we're going to see that. So what happens if our measurements are just not precise enough, or we're getting small differences at the 5th to 6th decimal place? How is that going to affect the forecast that we're making using our model? So first, we'll look at perturbing the initial conditions and how it affects it. But also, the model itself could have some errors in it in terms of the parameters, that beta, that sigma, that rho that we're using. What if experimentally we're just a little bit off in what those numbers are? So even if they change a little bit, how is a change in the model, in the parameters of the model, going to impact the behavior and our forecast of our state variables? All right, so now we can go into our main code and investigate the first issue. What happens if our initial conditions are a little bit inaccurate or even a little bit imprecise? Well, what's going to happen to our forecast? All right, so I'm defining the system parameters. Again, here I'm specifically using rho of 28, sigma of 10, beta of 8 over 3 for this model. And these particular set of parameters do kind of exaggerate or exemplify how nonlinear systems can behave. So I'm going to run this for t from 0 to 50, so that's our time. Again, for the sake of argument, let's just say that the base unit is days that I want to forecast out. So 0 is today, and then t equals 50 will be the temperature, humidity, air pressure 50 days from now, and then everything in between. I'm going to do it in fairly fine steps here. Because it is a nonlinear system, small steps typically will give me more accurate results. So I'll take pretty small bites out of it as I go through. So I will define it as going 0.01 in step size. All right, so first in line 12, I'm going to run what I'll just call the baseline system here. So I am going to run the Lorenz M file. Again, that's just setting up my x dots. And for time t, states x, and then I'm going to put in the rho, the sigma, and the beta as defined above. For the time span, they're all going to run for those 50 days. Now here in 12, I'm saying my initial conditions are 1, 0, 1. So again, this is the initial temperature, air pressure, and humidity, let's say. Now the 1, 0, 1 obviously doesn't make sense to have 1 degree, 0 air pressure, and 1 humidity, but in a real system, these are going to be scaled differently. This is just meant to be an example of how the system, a nonlinear system, is behaving. So the literal 101 values don't matter too much in what we're doing. And then what I'm going to do is I'm going to run it 3 more times, where the only thing I'm going to change in my system is going to be my initial temperature. Let's say x is just a little bit different each time. So we saw this before in the linear system. I'll just look at it now. So the initial conditions in the baseline system are always 101. That doesn't change. But what I'm doing for the 3 other systems is I'm adding just a little bit to x each time. So notice y and z are always initially 0 and 1. But every time I run this random, I get a number a little bit more, a little bit less than 1 for x. So I'm adding just this random number from a normal distribution with mean 0 and standard deviation of 1 times 10 to the negative 4. So actually that change, that deviation, is even smaller than we were seeing for the linear systems in the previous examples. So I'm going to run it 3 times with this slightly different initial condition on x. So a little bit more than 1, a little bit less than 1. I want to point out again and really emphasize that the only random thing that I'm going to be doing is setting the initial condition. If I run, let's say 12, 1,000 times, it's going to give me exactly the same answers each time because the solution to it is deterministic. It's completely determined by that ODE or that set of ODEs that I put in Lorenz.m. So in here, nothing is random. The next state is completely predictable based on the previous state, because that's exactly how the ODE solver is working. It uses one state, one time step to get the next to get the next. And that's what the ODE solver does. So the only thing that's random is that tiny perturbation on my initial condition. And this becomes important later when we really want to discuss the difference between complexity, which is what we're going to be seeing here, and randomness. All right, so I'm going to solve this 4 times for those slightly different initial conditions. We'll come to the perturbations on the parameters in the next example. And now I just want to plot what's going to happen. So before I do the animation, I just want to show this. I'm going to plot this in 3D since I do have three state variables here. I'm plotting the phase space. It's a space because of the 3 state variables. So I'm going to plot the current location of the baseline, which is going to be a green circle. I'm going to plot then the 3 others, a magenta diamond, a cyan square, and then a red star. And I'm going to track them as time moves forward. What is the current state of the first, second, third, fourth system? Again, all starting at almost identical initial conditions, and we'll see as time goes forward how their states are going to change. And the trace, the black line that's going to be made, that is made just from the baseline system, so we can see kind of a history of how that is acting. All right, so let's look at the animation that comes out of this. All right, so we can see that all 4 of those glyphs are kind of all bundled together. I'll make this a little bit bigger so we can see. And we're only predicting 6 days out at this time. So their states are more or less the same. They're all predicting the same temperature, humidity, air pressure, as we're now going 10 days in our forecast. So they're all tracing out more or less the same pattern. Their states are still pretty much the same. Okay, so we're hitting 17 days. We're about to go 20 days out in our forecast. And we're seeing that now the states are different. They are not all on the same trajectory. They have kind of exploded out here in what the predictions are that they're making. And they keep going around the track. And now the X, the Y, the Z states that each of these runs is predicting is going to be a little bit different to vastly different from each other. And we're at 40, 45 days, 50 days out, and we'll see where the prediction lies at 50 days. All right, so at 50 days, we have this little snapshot. We'll look at that graph later. This snapshot of the XYZ states from these 4 different initial conditions. And we notice they're all different, and they're all visibly different. We'll see in the time trace kind of how different they are. But thinking ahead, now, this is a very simplified version of the weather. I'm not using the correct parameters necessarily, but if we think in real life, just as weather is our example, we never see a 50-day forecast. We see maybe at most a 10-day forecast, 7-day, 5-day forecast. We're never trying to predict 50 days out. So just as a little teaser of what I'll talk about later, that's because the reliability typically is going to go down as our forecast moves forward. So these were so these all started at pretty much the same point, the X initial just a little bit different on each one. And we saw in the animation where the estimates started to go apart at maybe 17 days. Now let's look at this other time trace that I made. So here I am plotting the X, the Y, the Z versus time. Now here I do have it labeled in seconds, but days, it doesn't matter too much here. All right, so if we see the 4 different colors are the 4 different initial conditions that we had. Notice we can only see a green line because all 4 are pretty much right on top of each other until we hit, like we saw in the animation, about 17 as our time. And now we see this divergence of the trajectories. So they still are in the X, the Y, the Z, if we try to look them all at the same time, between like 17 seconds and even 20 seconds or so, or if we were thinking of days, they're not too far apart, but we are seeing a noticeable separation in the predictions in the forecast for the X, the Y, the Z. And then really after we hit the 20-day mark, we see that really all 4 of the predictions, the 4 different colors, they're not on top of each other. They're each kind of taking their own path, and the x values, let's just use this as an example. We're seeing on the blue one that it has an x value of 13.72. The xy is in terms of the horizontal vertical. So x of 13.72, let's just say that's temperature, whereas like the green line is estimating it at negative 14.4 if that were temperature. So vastly different predictions between even these 2 runs where the initial conditions were only slightly apart. And they're really never on top of each other again after they separate. So the temperature, humidity, air pressure estimates are all different. So what we see happening in this example, all of our initial conditions are very close to each other. Y and Z are identical for all 4 runs. X is different by only a tiny bit. And starting off, all of the runs are kind of on top of each other. They're all making the same predictions. This is akin to maybe a 3-day forecast, 5-day forecast. Generally, those forecasts are pretty good. And then we go out to something more akin to a 10-day, or if we tried a 15-day forecast, where now they're varying widely. Like I said, I'll get more into talking conceptually about weather forecasting after we get through these examples. But as time goes on, these 4 initial conditions that were all initially very close to each other diverge greatly. And that can be a hallmark of nonlinear systems. We have what we're seeing, the sensitivity to initial conditions. Even though at the start they were very close, by the end, they're very far apart.